we're coming back to an example we started last time, which didn't quite look like this originally. So the objective function we wrote down last time was, so this was an investment thing, right? You were trying to decide how much to invest in treasury notes, bonds, or stocks. And there were various rules, like you can't put too much into stocks, you can't put too much more into bonds than you put into treasury notes, etc. Originally, our objective function was like 0.03 x plus 0.04 y plus 0.06. So if you look into your notes, this is what you'll see from Wednesday. We were trying to maximize this function, which is like, so it was like 3% return on bonds, on treasury notes, 4% on bonds, 6% on stocks. But then if you just kind of multiply this out and rearrange things, you'll see that it's the same as this function here. Okay, so that's where this comes from. We also had some kind of thing like 30 minus x minus y is at least 3, because you have to put at least 3 million into stocks. And that just becomes, if you rearrange, it just becomes this. Okay, so this is like, it's not exactly what I wrote on the board last time, but it's kind of the same after you do a few rearranging things. Okay, so I've done a lot of, well, not a lot, but I've done a few examples, and shown you how to do them. So maybe this time, I'll give you guys a few minutes to think about this and try to get a solution to this. So remember, there's 3 steps. You want to graph the inequalities, you want to find the corners, and you want to evaluate it at the corners. So feel free to talk to each other or ask me questions or whatever. So yeah, so this is the problem that we're solving. And don't mind me, I'm just going to write the next problem we're going to work on, but feel free to ask me questions or anything. Any questions? Anyone solve it yet? No? Okay. Yeah, these things take a long time. But you're going to have to get quick at them because you're going to have them on quizzes and tests and the third test and stuff. So. And if you are really fast and you've already solved this one, then you can start working on the one I've written there. Any questions or anything? So we're just kind of working on solving this one. Yeah, since you just walked in. So for anyone who's graphed it so far, how many corners are there in total on the 4? Okay. Yeah, there should be 4. If my picture's right, then there should be 4. Oh, by the way, there was a sort of, I think last time it was mentioned some intuition about this one. It turns out your intuition is correct. So you're going to want to minimize your treasury notes and your bonds, and then so get as many stocks as you can, and then subject to that, do as much bonds as you can. But in order to know that that's the answer, technically you probably have to check all the corners and stuff like that. Otherwise, yeah, it doesn't really verify it 100%. Okay, so maybe I'll start drawing something here. Let's see if what you guys draw matches what I've got. So, got my x and my y. So the line x equals 3 is just, well, okay. One tricky thing is you got to kind of figure out what kind of scale are we dealing with here. I mean, I think I don't know, if I set y equals 0 in all of these, I think the biggest x value I get is this one. So this is my line x equals 3. This is my line y equals 3, right? Those ones are pretty easy. X plus y equals 27, or that's going to be the line which goes through this point and that point. Okay. Let's do this last one first, and then I'll come back to this one, because this one's kind of the same thing as what I just did here. It's x plus y equals 15, so that's like when x is 0, y is 15. When x is 0 or y is 0, x is 15. So I don't know where that is. It's somewhere like here, maybe. Okay. So this is the line x plus y equals 27. That's the line x plus y equals 15. I haven't graphed this one yet, so I need to do that. So it doesn't really help very much to put in x equals 0, y equals 0, because it just tells me the origin. So I need kind of another point. I don't know, when x is 15, y should be 30, which is just a bit above this board. So it's kind of like, I don't know. I mean, these pictures don't have to be absolutely perfect, but okay, and then we have to decide, so this is the line y equals 2x. We also have to determine which side of each line we're taking. But so x plus y is supposed to be at most 27. That's this side of this line. X plus y is at least 15. That's this side of this line. Y is at least 3. We've got this side of this line. X is at least 3. Y is at most 2x. For this one, we can't just plug in 0, 0, because that's on the line. So that wouldn't be a very good choice. But if we put in 15 for x and 0 for y or something, we'll see that it's true, right? 0 is at most 30. So we should take this side of this line. If you try to kind of put all of this kind of together and take the intersection of all the, everything's basically pointing into this box here. Okay, so this is, so some people said there were 4 corners. Is this kind of roughly what the picture looks like that you drew, or, yeah? Okay, so now we got to find these corners. Some of them are easier than others, like this is y equals 3 and x plus y equals 27. If y is equal to 3 and x plus y is 27, then x must be 24. So this corner is got to be like 24, comma 3. Okay, to say that again, so this is y is 3. So this is the point that's on the line y equals 3 and on the point x plus y equals 27. If x plus y is 27 and y is 3, then x has to be 24. So that gives me that point. Similarly, this one's like 12, 3. Again, this is because x is 3, and x plus y is 15, so x would have to be 12. Like, I guess these kind of things where you have like a constant line like this, crossing a slanted line, those are usually kind of easy because you can just say, oh, y is 3, and then x plus y satisfies the other criteria, so x has to be 12. These ones take a little bit more thinking. But we can just do that with Gauss-Jordan, right? So this one, for example, is y is equal to 2x, or in other words, y minus 2x, or yeah, okay, y minus 2x equals 0. And it's on the line x plus y equals 27. Okay, if I throw that in a matrix, we've got minus. One thing is you need to make sure you've got the right, so I don't want to put 1, so I want to be careful to make, I'm going to make my first column the x column, and this one the y column. Notice I've kind of got these kind of backwards in some sense, so you got to make sure you put them in the matrix correctly. Okay, and then I probably did this in a silly order, so let's switch these around. Row 1, switch with row 2. Row 2 plus 2 row 1. I guess, right? And then 1/3 of row 2. It's like 18 or something. Okay. Okay, so that's, the solution is x equals 9, y equals 18, I think. Did anyone else get this? Okay, and then this thing would be the same thing, except you just solve. I mean, actually, it's really close to the same thing. It's like the same equations, except this one's a 15, because it's, or is it? Yeah. You're on the line x plus y equals 15, and the line y equals 2x. So basically, the same steps will work. It's just that this is a 15 instead. So that's a 15. That would be like a 30. So y is 10. And x is 5. Probably you want to show your work and actually do this properly, but yeah, if you think about it, that's got to be the answer. Okay. So now, yeah, we just throw in the corner points into our objective function. So if I put in 12, 3, which is that one, right? I think when you compute the objective function, you get like 1.38. When I put in 24, 3, you're going to get 1.02. 9 and 18, I get 1.17. And then 5, 10, I get 1.45. Okay, so this is going to be the best answer. And that does agree with the intuition that we talked about last time. Like it was mentioned that, okay, it kind of seems obvious that you should put, if you have to put half the money in bonds and treasury or treasury notes, well, you should put exactly half, and you should put all the rest of the money in stocks. So you should put 15 million in stocks. And then you want to have as little as possible in treasury notes because they're not as valuable in terms of the interest. So you put like as little as possible here, as much as possible here of that 15. That's satisfying this inequality. And yeah, so it is kind of intuitive, but the thing is this without a shadow of a doubt, these calculations tell you that this is the absolute best you can do. There can't be any kind of other answer. Okay. And you could imagine maybe there could be some other rules here which then make it less obvious what's going to happen. So you may, yeah. Did anyone get this far to get the actual answer? Okay, so yeah, these things take a long time. Okay, let's work on another problem. So for this one, it was already set up, and you just had to solve it. Let's kind of do the opposite now. So here's a word problem, and what I want you to do is set it up. So set it up as a linear program. So set up a linear program to solve this. And if you're really fast, then try to solve it. So let me just quickly explain what the question is. So you're in charge of buying cabinets, filing cabinets for an office. There are 2 types of cabinets in the catalog, only 2 types. Type A takes up 6 square feet, like on the ground. So you only have, you basically have a limited amount of money, and you have a limited amount of floor space, right? So this takes up 6 square feet of floor space. Every one of these cabinets costs $100, and it holds 8 cubic feet of whatever you want, like files or whatever. So the volume is this, the area on the floor is this, and it costs $100. Type B has a slightly different area, 8 square feet. It costs twice as much, and it holds a volume of 12 cubic feet. Okay. And basically, you have a limited amount of money, so you only have $1,400. That's your budget. And you have a limited amount of floor space, right? There's only 72 square feet that you can use for the cabinets. So the question is, how many cabinets of each type should you buy? Like if you have a limited amount of money, a limited amount of space, you want, subject to that, you want as much volume as possible so you can store the most stuff. So the question is, yeah, how do I maximize the volume? So I want you to set that one up. And I mean, if you're really fast, then solve it too. Are there any questions about it? Yeah. Yeah, so you're not going to have to graph the cubic feet thing. So basically, yeah, you're constrained in terms of your budget, and you're constrained in terms of your like floor space, but then you want to maximize the volume. So it's kind of like here where we were like kind of constrained in terms of how many treasury notes, how many bonds. There were some constraints on that, and we had to maximize profit. So we didn't have to graph profit on this graph. So now your volume becomes like your profit from before. So So what are people using for their variables? Like what does x and y represent? Yeah. Oh, sorry. Oh. Oh yeah. So yeah. So like so these are representing how many of type, you know. Yeah, that makes sense. And then you've got constraints for the, yeah. Yeah, exactly. So, right, so here you would, we're being asked to maximize the volume. So we're maximizing 8x plus 12y. Right, 8 comes from here, 12 from there. And then subject to yeah, so we've got a budget and we've got a space constraint. So our budget tells us that 100x plus 200y should be at most 1400. And then our space constraint tells us that 6x plus 8y should be at most 72. Because every filing cabinet of the first type is going to use up 6 in area. The second type is going to use up 8, and you can't use more than 72. Any other constraints that I might want to have here? Yeah. Yeah, you can't be like, I'm going to buy -5 of one and 12 of the other or something. Right, so these have to be at least 0. This is always a sort of thing you have to think, like you have to think at some point, do I need this, right, this constraint? With the investment problem, we didn't need that constraint because there was already a constraint saying everything had to be, each type had to be at least 3 million. So we didn't really need this, but so if this question already said, oh, you have to buy at least one of each type, then we would have like x at least 1, y at least 1, and you wouldn't need to say that they're at least 0. But yeah, if it doesn't say anything, then you should probably think, do these need to be non-negative? Okay. So just to kind of quickly graph these. So I think it kind of looks like this. And you've got like so this is kind of what your region looks like. This is the point 12, 0. This is 0, 7, right, 0, 0. Right, so that's kind of 3 of your 4 corners. The last corner is, so apparently this is 8, 3. Okay. So by the way, this is the line here. 100x plus 200y equals 14. And this is the line 6x plus 8y equals 72. And yeah, if you solve this system of equations, then you'll get 8, 3, I think. Okay. So then to solve this, to finish it off, you just plug these values in, and it turns out if you put in 0, 0, you get 0. Obviously, it's not a good idea to buy no cabinets, so that's kind of obvious, right? That's not going to maximize your volume. 0, 7 would be 84. 12, 0 gives you 96. Getting better and better. Then 8, 3 gives you 100. Okay. So the best is to buy 8 of type A and 3 of type B. And by doing so, you're going to get 100 cubic feet, right? Okay. Obviously, though, like, yeah, if your parameters change a bit, this is going to change, right? If one of these cabinets goes on sale for cheaper, then you've got to, you know, it changes things and whatnot. One thing is, like, this is pretty lucky, right? There's not really a good reason why these numbers would be integers, like whole numbers. Basically, this question was cooked up that way. But like, in principle, you could have ended up having your constraints giving you a corner here that was like 8.1 and 2.9. And then it becomes a little bit trickier. Like, how do you can't really buy 8.1 cabinets, right? So this was a little bit lucky, but yeah, it works out. Okay. So for the last 10 minutes, I'll just really briefly, well, actually, are there any questions about any of this linear programming stuff? Because this is the end of linear programming. Okay. So we're on to the very, very last topic of the course. Okay, so this is something called Markov chains. Here's a warning. So there is I think there's a chapter in the textbook about Markov chains. Do not go to it. Do not. I mean, it's covering a different problems on Markov chains than what we're going to cover here. This is a big subject. You could cover it from a lot of different angles. Yeah. The ones in the textbook, they're not going to be useful. But there's kind of extra stuff in the handbook about this. So this is 100% like, so basically use the handbook, which is on Brightspace. Under, if you go on the Brightspace, there's a section called Getting Started. It's a bit late to be getting started now, but so use the handbook only. So not, you know, MyLab Math, not the textbook. It is potentially confusing because there literally is a section or a chapter in that textbook about Markov chains, but it's covering the wrong parts of Markov chains. Okay, but there's most of the handbook things, they're quite, you know, short descriptions, but this one, if you look in the handbook under Markov chains, it's a longer thing explaining, you know, like a textbook, basically. Okay, so this is going to be a nice topic because it's going to bring together lots of different things we've done. Matrices, systems of linear equations, probability, it all kind of gets wrapped up together. Yeah? They're going to use basically they're going to use questions that come from another book that covers the right stuff. So they're going to be similar to the, I guess they're going to be similar to questions you'll see in the handbook, actually. They're still going to be on MyLab Math, yeah. Yeah, it's just the study guide and stuff you can't really use for this, yeah. No, you shouldn't, yeah. Basically, don't use MyLab Math for this part, except for doing the quiz. So just go right from the handbook. So kind of roughly speaking, a Markov chain well, it gives us a simple way. So it's a simple, sometimes too simple, but it's basically a simple way to model kind of mathematically a system that changes state. So I'll put that in quotes as well. Over time. So this is a very vague statement. So let's think of an example of something you could try to model with a Markov chain. I'll say that Markov chains are not always a great model for things, but it does give you some kind of useful information. So one thing you could model is the weather. So let's say, over the past year, in a particular city, for each sunny day, the probability that the next day is sunny or maybe not probability, sorry. I should say that 60% of the time, let's say, so sorry. It's technically maybe not a probability, but 60% of the time, the next day was also sunny. Okay. So if let's say we look at the data from the whole year. I don't know how you quantify what means sunny, what day is sunny and what's not. But let's say we have some measurement to say that day was sunny, that day was sunny, that day was not sunny, and we can classify them. And this is saying 60% of the time when it was a sunny day, then the next day was also sunny. And let's say that for each not sunny day, each non-sunny, so let's just say there's only two types of day. The next day was sunny 45% of the time. Okay. So given this data for over a whole year, if this pattern kind of continued, you can kind of you can use this to kind of model how the weather is going to change, right? You could say, okay, what is it like today? Is it sunny or not? And then you could say, okay, if it's sunny, it's got a 60% chance of being sunny the next day. Right, and this would give you, it's a very crude model of the weather because that's not really how weather works. It doesn't just flip a coin and then 60% of the time it's going to be sunny the next day or something. But you could kind of model it this way. And here's kind of a question we're going to be able to answer. If this pattern continues forever, what percentage of days will be sunny in total? So I'll say, what percentage of days will be sunny in the long run? So that means if we kind of let time run to infinity, right, and I count the number of sunny days as a proportion, like what percentage will be sunny? And it's not obvious from this. It's not going to be a nice number like 60% or 50% or 40%. It's some kind of wacky number, but if you study this as a Markov chain, then you can figure out the answer. So that's what we're going to be doing.